Hey everyone, I am Jain. Welcome to Jain AI Lab. Ever wondered how self-driving cars classify objects on the road? Well, today we will explore the part 3 of support vector missions and algorithm behind such applications. Last time, in part 2, we understood how to formulate the SVM Lagrangian function and the KKT conditions. Today, we will explore the Wolfe dual problem and the convex optimization algorithm with code. Guys, it's very important to understand that mathematics is a tool will help you to stand out. Since AI is booming, everyone is rushing to learn AI, but only a fraction of them understand the mathematics behind it, the mathematical backbone. So it's very important to understand a very important video. So watch the video till the very end. Let's get started. I'm very excited. Guys, before getting into today's video, let's have a recap of part 2. We understood the method of Lagrange multipliers and we applied it on SVM and we came up with this optimization problem subjected to this constraint as you can see on the screen. And we optimize it. We try to find the W and D using KKT conditions. And if you don't know what are KKT conditions and why we are using KKT conditions, please watch part 2 and come to this video. Now, on solving KKT conditions, we came up with these results. W is equals to summation of alpha 1 to alpha m, alpha I yi xi, and summation of alpha I yi equal to 0. And on substituting this W in this Lagrangian function, we came up with this W of alpha. I renamed it as A. Then Then to compute W, we need m alphas, right? Alpha 1 to alpha m because we want for every data point Lagrange multiplier is associated with it. So we want to have m alphas, m alphas. But we took one example where we want to find two alphas. For getting two Lagrange multipliers, we solved four cases, right? Then imagine, guys, we want m alphas. If we want to solve this task, it will be very tedious, right? It will be very tedious to solve manually. Think about it. So, what is the solution? What is the solution? The solution is to create an algorithm and use that. Now, the algorithm is already present, convex optimization, CVXOPT, but how to use that? Now the Wolfe comes, the another scientist comes to Lagrange and the KKT says, and he says, hey, reformulate your optimization function to my optimization function and use the algorithm. You can get the solution. He says like this. Now let's get into today's video. The Wolfe dual problem. The Lagrangian problem has m inequality constraints, right? Now, where m is the number of training examples, as I told you before, and typically solved using its dual problem. If the Lagrangian problem has m inequality constraints, we will be using the dual form to solve it. What is duality principle now? You will tell what is duality principle. Okay, let's see. It is an optimization problem, can be viewed. It says duality principle says you can you can view it in two perspectives. An optimization problem can be viewed in two perspectives. The first one is the primal problem, a minimization problem in our case, and the other is the dual problem, which is a maximization problem. We can view the optimization problem as the primal problem or the dual problem. What is interesting is that The maximization of dual problem will always be less than or equal to the minimum of the primal problem. Let's have a intuition in this and we'll come to this again. Now let's recall the Lagrangian problem. What is our problem? We want to minimize this norm of w square by 2 subjected to this constraint, right? Subjected to this constraint. You can see on the screen. And I given a name to the constraint gi of w, and this is our gi of w, and our Lagrangian function is equal to f of w. Means norm of this plus c. In last video part 2 I used the negative sign here. Now I am using the positive sign. Why, Jane? Why are you using two different signs? Hear me out. It doesn't matter which sign we are using. It does not affect on the output, the values of w and d. It's the mathematicians told us on experimenting. They solved so many problems. They came and they are telling you can use any sign, and this is our Lagrangian function. Now we are defining one function. Now we are defining, guys, now we are defining, and we will now understand what is primal problem. Now we are defining something. Theta p of w is equal to maximum of this function, maximum of the Lagrangian function. How we will get, where we will get the maximum? We will get the maximum of alpha. We want to find the alpha I such that this Lagrangian function will be maximum. That is our aim. This is what the theta p of w is saying to us. Now let's substitute what is the Lagrangian function. I substituted it, f of w plus this. I substituted. You can see that, you can see it on screen, right? Now let's understand. Our GA of W, nothing but this, is less than or equal to 0, right? Now let's see what if it violates the condition. If it is greater than 0, what if, guys? If it is greater than 0 means theta p of w equal to infinity, then you will say how. Let's understand. See, what is our theta p of w function is saying us? The function f of w plus summation of alpha I gi of w should be maximum for what value of alpha I. Now, if gi of w is positive, means this term is positive, means what value of alpha I will choose, and I know alpha I value should be greater than equal to 0. I will choose the maximum alpha I, right? It will be infinite. I can choose maximum alpha I. So if I choose a maximum infinite value, it will become the infinite, right? Then theta p of w. I hope you understood why gi of w greater than 0 condition violates. Why we are getting theta p of w equal to infinity? Because I can choose alpha I, which is very large, huge number, so that it will become infinite. Now if it's, let us say this condition is satisfying, gi of w is less than or equal to 0, then to make theta p of w maximum, we have to make this as maximum, right? And we know gi of w is less than or equal to 0. We have to take alpha I equal to 0. Now you say how, why alpha I equal to 0? Since it is because gi of w is less than 0 and we want to maximize. If you want to maximize, you take the value of alpha I as negative jnth. What will happen? See, guys, alpha I is greater than or equal to 0. We cannot take negative values of alpha I. The starting is 0 only. We cannot go to the negative part, so that it will be maximum. So if you take alpha I as 0, then it will be maximum, right? That is the reason alpha I is equal to 0 when gi of w equal to negative. Now what is, that is the reason. Now what p theta p of w is equals to, it is nothing but f of w only, right? It is only now f of w. This term became 0 for this maximization problem. So or theta p of w is equal to f of w when it satisfies the condition, and it's when it violates the condition. Now the primal problem is defined like this, guys. We defined a function before, which is a primal function. Now the primal problem is defined like this. We want to minimize the primal function for what values of w and d. For what values of w and d we will get the minimum of the primal function. That is how the primal problem is defined. If you want to understand why primal problem is defined like this, why dual problem is defined like this, it's out of scope of this video, because we you have to learn the convex optimization. NPTEL lectures are there, you can learn from that. I too don't know what is convex optimization. There are so much in depth. If you want to go to depth, there is more depth, guys. Now let's understand what we want to understand SVM. Primal problem P star is equals to minimum of this theta P of W. I just substituted the primal function here. Maximum of alpha I greater than equal to 0. Now this is our primal problem. Now how dual problem is defined? It's defined like this. Just alt let's exchange this maximum minimum. Maximum and minimum. Maximum of alpha I greater than or equal to 0, and minimum of w comma d of the Lagrangian function. Now, this minimum of w comma d of the Lagrangian function, I defined it as dual function, and this d star is equals to maximum of alpha I greater than or equal to 0. This is how the dual problem and the primal problem is defined, right? Now, the fact which I discussed before, which is the maximum of dual function will be less than minimum of dual function. See, let's take one example. Dual problem will be always less than or equal to primal problem. Maximum of x, maximum minimum of cos of x plus y will be less than or equal. Let's see whether it is satisfying the condition or not. See, what will be the maximum of cos value? This is plus 1, right? Because its range is from minus 1 to 1. Maximum I have written, and I have written the minimum value, and maximum of minus 1 for what value of x? It is not depending on anything, so it's minus 1, it is 1, so it is conditional. And it is not only satisfies for this function, it will satisfy for any function, guys. We should know the proof. To know the proof, learn convex optimization. If you want to understand the convex optimization certain topics, please comment down in the comment section. I'd be very happy to discuss. Now, in our case, we are trying to solve convex optimization problem. And you will question, what is convex optimization problem? Convex optimization problem is nothing but when we have a function, let's suppose x square is there, right? See me, x square is there. And if you define a line segment between two points, the minimum is present one. We have only one minima, right? See, this is our function, and we drawn a line segment here. We have a minimum here, only one minimum. On drawing the line segment, we should have only one minima or one maximum. We should not have so many minimas, like there will be global maxima, there will be global minima. That those should be not there. Only one minima should be there or one maxima should be there. That is how convex optimization problem is defined. In our case, we are trying to solve convex optimization function. How I said it is a convex? Because w square is nothing but a function like x square, right? Its curve will be like this. It's graph. That's why I told you. Convex optimization problem, and the Slatter's condition holds. Slatter's conditions holds for affine constraints. Nothing but hyperplane constraints. We have the hyperplane constraint, right? J of W. That's only I'm talking about. And the Slater condition holds. This means that solving a dual problem is same thing as solving the primal problem. Now, why you are concerned about dual problem and primal problem means, I told we want to reformulate the Lagrangian function to the to the dual form so that we can use the algorithm CVXOPT. Now, to have the to get the dual form, it's easier, guys. It will be easier to solve the dual. We have to check primal is easy to solve or dual form is easy to solve. We have to check that. The Lagrangian dual problem we wrote before. See, this is we already solved this. Now see, d star, the dual problem, maximization of alpha, minimum of w comma d. This is, see, we are minimizing this. This is our Lagrangian function, right? Before we solved this and we got a. I showed you before. See, this is our a. This is our A. Wait, let me show you. See, this is our A. We substituted W on Lagrange function and we got this W of alpha. See, Wolf says, hey, you don't do everything from the scratch. What you have done is correct. You change that. You reformulate that to my in the dual form. Now we are doing that only. We got this W of alpha. See, W of alpha. We got that. We got that. Now we just have to maximize that, right? We just have to maximize this with respect to alpha I. This is a Wolfe dual Lagrangian function. Now, this W of alpha is called as Wolfe dual Lagrangian function. The optimization problem now is called the Wolfe dual problem. We want to maximize this W of alpha with respect subjected to constraint. See, alpha A should be greater than or equal to 0. Alpha is greater than or equal to 0, which is telling the dual problem is saying for us this should be greater than or equal to 0. And we had the another constraint on solving this, we got this right. We got this result. And why I'm not taking this result? Because it's not that useful. We want this alpha I. We substituted and we got this right. We got this W of alpha on substituting it. So I'm taking only this result as a constraint for this problem W of alpha, maximizing this optimization problem. This is now became an optimization problem with these two constraints. The main advantage of the Wolfe dual problem over the Lagrangian problem is that the objective function W now only depends on the Lagrange multiplier. See guys, it's now W of alpha, not the W L of W comma D before. See here, see it is depending on W, D, and alpha. Now W is depending on only alpha, Lagrange multipliers. It's our main advantage now. The very important point is this formulation will help us to solve the problem in Python. I told you right. We want an algorithm to solve the Lagrange multipliers and to get them. Now, what to do once we have the Let us suppose we have the Lagrange multipliers. Now, what we have to do? Then we can easily compute the W, right? Because we want W. Alpha is because yi is nothing but the labels of the given data. Xi is nothing but the data itself, and this you can compute, right? Now, how to compute the D? What is how to compute the D in a hyperplane? Hyperplane equation is W dot X transpose plus D equal to 0, right? How to get the D? Once we have W, we know the closest points to the hyperplane will satisfy pi plus. We know, right? Pi plus closest points are nothing but the support vectors itself. W plus, this is our pi plus equation. Let me show you the pi plus. See the equation, the first part. Guys, watch the series videos in the series. Watch part 1, part 2, then come to this video. Let me show you. See, this is our pi plus. This is our pi plus. The points that are lying on pi plus will satisfy the equation, right? This equation will be equal to 1. W transpose dot xi plus d equal to 1, right? That only I wrote. And also we know the constraint. We have the constraint, right? This all the positive points, all the labels, all the data points which have positive label will satisfy this. Also the negative points also. This is a combined equation for both the labels. We discussed it in the part 1. Go and do watch it, then you will understand better. The points lie on the pipeline will satisfy this. Yes, it will. They will satisfy. Now we multiply y on the yi on the both sides, because yi values are 1 or minus 1. Y square will be 1. So we got this W dot xi plus d equal to yi, and d is equals to yi minus W dot xi. What is this xi? This xi is the support vector. Why I am saying it is a support vector? Because this equation is satisfied by only the support vectors, right? If it is not a support vector, it should be greater than 1. If it is, if we, or less than 1, right? Now, instead of taking one support vector and calculating d, we instead take the random. Instead of taking the random support vector, we take the average, which provides the numerically more stable solution. Now d is equals to 1 by s. What is s? S are the number of support vectors. Summation of I equal to 1 to s yi minus summation w dot xi. Now you will question, you may have the question, how to get the support vectors? What are support vector, guys? Initially, the support vector mission do it will randomly initialize the values of w, right? And it will have the hyperplane equation. What it will do, it will take the distance, it will take the distance. Let me show you this figure. It will take the distance of the hyperplane, that is the randomly defined hyperplane, to every data point. Every data point it will take the distance, and the data points which has the minimum distance, and it will consider them as the support vectors. I hope you understood how we get the support vectors. It will randomly define a hyperplane, and it will take the distance to, it will take the distance, it will calculate, and it will measure which is in the less distance, it will take them as support vectors. Now we got d as well. And finally we want alpha a side. We have not discussed it. Using the support vector we are able to find, see, using the support vectors we are able to find the equation of the hyperplane. This is the reason why we call them as support vector missions, as support vector missions. I hope you understood why we named them like this. Now finally, let's get into the code. Before going to the code, we want to formulate, right? We want to formulate it. Still there. If you're watching the video till now, hope you're enjoying it. Please like, share, and subscribe. Let's see. Solving the SVMs with a QP solver means it is a quadratic programming solver, right? Pro, it is a quadratic programming problems. No, CVXOPT is nothing but solving the convex optimization problems. See, it says it will solve, this algorithm solves the minimization problems which will be in this form, minimization problem which will be in this form. No, it is not looking like ours, right? This x is, now let's rewrite this x as our alpha. See, it will look like this: minimization of alpha half into alpha transpose p alpha q trans subjected to this constant g alpha less than or equal to h a alpha equal to, we want to find the what are this p, what is p, what is q, what is g, what is h, what is a, what is b, for our problem, for our w of alpha. Now we will change the Wolf dual form from maximization. See, Wolf dual says we have to maximize, right? Now this QP solver says we will do for the minimization. We will do for minimization. Now what we have to do? We just have to multiply the Wolf dual formulation with minus one. See, minimizing the alpha, I was just multiplied with minus one. Before this alpha is positive, now it is became negative, and I also multiplied with the negative one with for the constants as well. Now alpha I will be less than or equal to 0, and see, multiplying this is negative is same as before, right? Now this is our problem with respect to the quadratic programming problem. Now we want what we want. We want P, Q, G, H. This is our aim, right? This is our aim. This is our aim. Now, then we introduce. We will say this all the alpha is as alpha, one alpha, a matrix which is a column vector, alpha one to alpha m, column vector, and yi, and v, and W not C alpha, alpha 1 to alpha m, y I define as C, all the values of labels as the column vector, and the gram matrix K. See, I am defining a matrix K for the all possible dot product. See guys, this xi dot xj is nothing but dot product, right? Dot product of every vector with all the vectors, right? That is I defined as K, and this is our matrix. And alpha j equal to alpha transpose, I am defining alpha j equal to alpha transpose, because what I want to do, I have to write this, I have to make it in this format, right? I want to make this in this format to understand that alpha j equal to alpha transpose, alpha I equal to alpha, and ya into yj equal to y transpose into y, because that is multiplying. Which, see, why are doing transpose? Because matrix multiplication, because now we make them as a matrix. That is why y into y transpose, and xi at xj as k, and just substituting these values in this, we came up with this, guys. We came up with this, minimizing half into alpha transpose, and this y transpose k alpha minus. Now it is looking like, this, right? Now it is looking like this. Now just compare these two and find g a p q b. I just compared and I got these values, guys. P is equal to this, K is Q transpose equal to minus I, G is equal to minus I. You just have to pause the video and come back. See, notes will be in the description box. You can download that. I have my own portfolio. You can download all my notes from the AA handwritten section page. Okay. See, I just compared. Now let's get into the code example. See, if you are watching the video till now, it's great. You're doing a great job. You'll really become a top-notch data scientist. I promise you. Now let's get into the code. See, CVXOPT is the algorithm. I imported it and I have defined a function. I just asked the Gemini provision model, the Gemini model. It is given me the code. That's all. See, the P is defined as matrix dot np dot outer y comma y into dot np dot product of this x in x comma x transpose, because we are multiplying every vector, we are doing the dot product of every vector with other vectors, right? See, it is just this code. We know what is p. See, this is our p, right? This is only, this is y into y transpose is our label, with our label, and we are multiplying with the k is nothing but the dot product of one vector which all the vector, this matrix, that is only defined, that is only written here. In terms of code, we are converting the mathematics into code. That's all, guys. If you want to understand anything, everything from this code, you just see why q is defined like this, because the q is minus I identity matrix, and they are trying to define that one. They are trying to define minus 1 into np dot ones. See, in n sample, see, I took the small samples, only three data points, and whose labels are minus 1 comma 1 comma 1, and c is a parameter that we have defined. See, we will define p q g h a b like this. I will share this code in the description box. Please go and check it out. And we will use the solver, cvx solver, and we are getting, see, we are getting the alphas, 2.5 to 10 power minus 1, 2.5 10 power minus 1, 2.9 to 10 power minus 1. See, guys, see, we're getting the alphas like this. For any, for a big data set also, you can able to find it. You can able to find the Lagrange multipliers, any number of Lagrange multipliers using the algorithm. And also another examples I had. See, this is our training data, and you can use the solver. See, I have defined the function in a clear way. You can get this. See, explore this code, guys. It's just a code from the mathematics. It derived from the mathematics. Explore this and understand. I hope you understood the hard margin SVM in three parts. If you understood something, if you got any value, guys, please like, share, and subscribe. Thanks for watching.